Hello students, this is the next video in continuation to the previous video. I told you the p-type semiconductor material. Let me tell you now the n-type semiconductor materials. In n-type, I told you previously that we use pentavalent elements along with the pure semiconductor. These pentavalent elements are such as phosphorus, arsenic, antimony, bismuth. I'm taking an example of phosphorus element. When this phosphorus is added in a ratio of, in a standard ratio of 10 to the power 8 is to 1. Okay, I'm taking phosphorus, one element of phosphorus with 10 to the power 8 atoms of pure semiconductor, and that semiconductor I'm taking here as silicon. Okay, so around this phosphorus element I'm taking 4 atoms of silicon, and I'm showing you a covalent bond diagram. So here is a phosphorus element. It has 5 valency. That means it has 5 electrons in its outermost orbit. And here we have silicon atoms. These silicon atoms, semiconductor atoms, have 4 valence electrons. So here I'm showing you these electrons. Okay, so with this diagram, we can observe that for a phosphorus atom, there are, how many electrons are there in total for a phosphorus atom? Let me count, 1, 2, 3, 4, 5, 6, 7, 8, and 9. This is the 9th. This is an extra electron which will come into the next orbit. It will be shown in a new orbit. So this is called the excess of electron. This is called excess of electron. Excess of electron. Excess of electron means excess of negativity. Therefore, it is called n-type semiconductor since it has the excess of negativity. The other name of n-type is called is a donor type. Why is it called donor type? Because since it has one extra electron, it will always try to donate this electron to acquire stable structure. So in order to become stable, it will have the tendency to donate this extra electron. Therefore, its name is donor type. So I hope you have got the concept of p-type, n-type, acceptor type, and donor type semiconductor. Now, to begin the subject, we have to go to review p-n junction. So the p-n junction is simply formed by adding a p-type crystal with n-type crystal, and this can be an alloyed junction, diffused junction. There are so many fabrication processes of having a p-n junction. So and there may be any process to p-n junction, but let me tell you, in a p-n junction, if let me first show you a p-type crystal and n-type crystal. N-type crystal. P-type crystal and n-type crystal are just opposite to each other. In a p-type crystal, it has the tendency, it is called as acceptor type. So if it accepts an electron, it becomes negative ion. For each hole, it has a negative ion. For each hole, it has a negative ion. This ion is obtained by accepting an electron. So if I show you hole, and for each hole there is a negative ion, and along with that there are few minority electrons also. This is something we have in a p-type crystal. Similarly, in n-type crystal, it has got the name of donor type, so it has the tendency of donating an extra electron, and if it donates an electron, it becomes positive ion. So the number of ions is equal to the number of electrons it donates. So it has positive ions, and these number of ions are equal to the number of electrons, which I am showing by the dot shaded circles. And there are few holes, which gives you the minority charges. So these are the two p-type and n-type crystals separately. But when we use a junction, p-n junction, by using junction formation processes, whether it is an alloyed junction or diffused junction or any other form of junction formation process, we get a p-n junction, and that p-n junction is nothing but the diode. So now we go to p-n junction. So I'm going into the subject now. I hope I have given a sufficient amount of review of semiconductor, electronics, p-type, n-type, and then I'm coming to the subject, which is the first topic of our subject, is review of diode. Diode is nothing but a p-n junction. Diode is nothing but a p-n junction. So I just showed you a p and n crystal, and now I'm trying to show a p-n junction. Okay, just a second. Let me make it a little broader. Trying to show you p-n junction. So in a p-type semiconductor, as I just showed you, in a p-type crystal, there are a number of holes, which are positive charges, and for each hole there is a negative ion, and there are few minority charges as electrons. Similarly, in case of n-type semiconductor, we have free electrons. These are free electrons, and for each free electron there is a positive ion. This I'm showing you here. I'll tell you why I'm drawing these ions in this region only, and a few, very few number of minority charges as well. So this is my n-type semiconductor. So this particular region where I'm drawing, where I'm showing the ions only, this particular region is called Immobile Ion Region or depletion region. This is the region where the ions exist, where the ions remain. As we all know that the ions are much heavier particles compared to electrons or holes. Ions are nothing but these stable atoms. When an atom releases or accepts an electron to become stable, it becomes ion. So ions are nothing but the atoms which are stable, and they are much heavier compared to electrons or holes. So since they are much heavy, they cannot cross this junction. They cannot cross the boundary of p-type and n-type semiconductor. Since they have opposite polarities, they attract each other and they remain within their boundaries. They are not able to jump or cross the boundaries because of their heavy weights, because of the huge amount of energy required for them to move from their region, from their boundary. So these ions remain within a layer. This is called depletion layer, or just because they cannot move, it is called immobile ion region. This is also called a barrier region, and this barrier region requires a certain potential. Just a second. This barrier region requires a certain potential to overcome it, and therefore it is called potential barrier. It has got a potential to oppose the majority charges. It has got the energy to oppose the majority charges of p-type and n-type semiconductors to cross the junction. Therefore this region is also called potential barrier region. So I told you the three names of this region. One is depletion region, potential barrier region, or immobile ion region. Because of this region, we do not get sufficient magnitude of current through a PN junction if we do not apply any external voltage. Only a very small drift current flows initially, which is of such a small magnitude that it is of no use to us. So in order to make it operate, we have to apply external voltage. And this application of voltage is called biasing. So we are applying external voltage to a PN junction in order to make it work. This application of voltage or biasing is done in two ways. One is called forward biasing and the other is called reverse biasing. So the forward biasing is obtained by adding positive terminal of a battery to the p-type material and negative terminal of the battery to n-type material. By doing so, we get a sufficient magnitude of current through the device. How do we get the flow of current through the device? Let me tell you this. So initially, we were having a barrier region at the junction which was not allowing the majority charges from P and N-type materials to cross the junction. Say, for a P-type material, if you focus only on P-type material, the holes, which are the majority charges of the P-type material, were repelled by the positive ions of N-type semiconductor. Similarly, the electrons from N-type semiconductor were repelled by the negative ions of P-type semiconductor. So they were flowing in opposite direction to the junction. They were not at all flowing towards junction, but they were flowing opposite to the junction. They were rather pushed back away from the junction. Now, this external voltage or bias is nothing but electromotive force. Voltage is also called electromotive force. It is nothing but a force applied on the electrons for their motion. So this force means the positive terminal of the battery when applies force on the holes of p-type material, they are pushed towards junction. Are you getting this point? When the positive terminal of the battery applies a force, it repels because they are of same polarity. It repels the p-type material, the hole, towards the junction. Similarly, the negative terminal of the battery applies a force on the electrons. And again, they are of same polarity. They are repelled towards junction. So both majority charges, whether holes from p-type and electrons from n-type, are pushed towards junction by the forces applied by battery. This force, the magnitude of this force is much more than the magnitude of the force applied by the ions in this layer. Earlier, the positive ions were repelling the holes and negative ions were repelling the electrons of n-type. Now, the battery's positive terminal of the battery is pushing holes and negative terminal of the battery is pushing electrons of n-type semiconductor towards junction. So there are two forces acting in opposite direction. One force applied by the battery towards junction, another force applied by the ions opposite to the junction, and we can easily observe that the force of the external battery is much greater than the force applied by the ions. Therefore, they will easily cross the junction. The holes from the p-type and the electrons from the n-type will cross the junction easily if the applied amount of force or voltage is greater than 0.7 volt for a silicon material and 0.3 volt for a germanium material. So in that case, it will easily conduct. So the concept is that if positive terminal is connected to p-type, negative terminal connected to n-type, and the amount of voltage is greater than 0.7 volt or 0.3 volt for silicon or germanium, then there will be a sufficient amount of current flowing through the junction. This current is called the main current or forward current. Okay, main current or forward current. The direction of current is always from positive to negative, from P to N. It is of the order of milliampere. This magnitude is of the order of milliampere. So this is a switching done. In this case, the device becomes on. The diode, the symbol of the diode, if I show you, this is the symbol. Okay, let me draw you again. Okay, the symbol of diode, I was trying to show you the symbol. So in this symbol, this is called anode. This is called cathode. Okay, so the positive terminal is called anode, negative terminal is called cathode, and if it is forward biased, means battery positive is connected to anode and negative to cathode, then it behaves as a switch which is short circuited. Behaves as a switch which is short circuited. Okay. So in this case, the current is full and the resistance is minimum or ideally zero. Okay. So this is the concept of forward biasing. Next comes is the concept of reverse biasing. Okay. For the concept of reverse biasing, let me again draw a PN junction. Okay. Reverse bias. For reverse bias, let me again take a PN crystal. But in this crystal, what we'll do, okay, this is my junction, this is my terminal, this is a positive terminal, this is P-type semiconductor, this is N-type semiconductor. Okay, just a sec. This part is, okay, now I am reversing the polarity of the battery. Now I'm reversing the polarity of the battery. We reverse bias. So in this case, what will happen that the majority charges, whether they are holes or electrons of n-type p-type and n-type semiconductor, will come towards happening to the system. Okay, here we have negative ions. There, as I mentioned, there's few electron in p-type and few holes in n-type. This we can also draw. So now, with this, what is happening actually, the negative terminal of the battery is attracting the majority charges of the p-type material which are hole towards it and repelling the minority or negative ions towards junction like this. Similarly, the positive terminal of the battery is attracting the negative charge, the majority charge towards its terminal and repelling the positive charge or ions towards junction. So at the junction, what we can see, just a second, okay. So at the junction, what we can observe is that the width of potential barrier, that the width of the junction is increased. The width of the junction has increased. The immobile ion region has become much more effective and strong so that none of the charges from p-type or majority charges from p-type and majority charges from n-type will be able to cross this barrier region. So the overall behavior is that there is no flow of current, then there is no amount of current that flows through the junction in case of reverse bias ideally. But as these immobile ion region, in the case when these immobile ion region cross this barrier, this situation is called the breakdown situation. The breakdown situation, when the immobile ion region cross the barrier layer, they move across the junction, resulting into a sufficient magnitude of current, not equal to the forward current, but the current of the order of microampere. That situation is called breakdown, that we'll study later. And in the breakdown phenomena, we get the flow of current due to the charges inside the depletion region. Okay, so ideally no current flows in reverse bias and maximum current flows in forward bias. We can also call there is a small amount of leakage current, very small flow of leakage current. So in case of, if I show you the symbolic representation of reverse bias, it will be like this, having negative terminal connected to anode. Just a second. Let me draw it. Okay. So it will be having a negative terminal connected to anode and positive terminal connected to cathode. Okay, this is called V reverse bias, and in this case, no current. I'll show you that the device behaves as a off switch. The device behaves as an off switch. So for that, if I show you, the off switch is nothing but the open switch. This is my off switch or open switch. Open circuit भी बोल सकते हैं इसे. This can also be called as open circuited, and the previous case was called as a short circuited. So ideally there is no flow of current in case of reverse bias. I equal to 0, resistance is maximum, depletion width increases, depletion width increases, and device behaves as off switch. Okay, so this is the comparison of behavior, the study of a PN junction under forward and reverse bias conditions. So after this, we will go to the next topic, which is the current VI characteristics of PN junction, then its breakdown, and then we'll go to its switching action into the next videos. So for now, it's bye.